Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to just do a few proofs with the rank theorem that I kind of think are just important to see. And for any of these, definitely, as always with proofs, the most important thing is to think about like what something is saying. So this one says you have two square matrices, both full rank, right? And we want to just show that the product of them also is full rank, okay? So I'm going to start off, by the rank theorem, right? If A and B are full rank, then their respective nullities are both 0, right? Because basically n plus nothing equals n. So now I'm going to let x be in the null space of B. So by definition, bx equals 0. Note then that AB x equals a times 0, right? Just multiplying by a on the left. And actually, I think I'll do it. Yeah, I'll do it that way. This is basically equivalent, right, to ABX equals 0. So the idea here is, we know that, if x is in the null space of B, the only thing it can be is the 0 vector, right? And so now we're seeing that x is in the null space of AB, so that x also needs to be the 0 vector. So you can just say since x was in the null space of B and the nullity for B was 0, we know x is the 0 vector. And likewise then the nullity of AB is 0, okay? Then just lastly, by the rank theorem again, we get that the rank of AB is n, right? And that does it. All right, so here we want to show that for some square matrix, ATA is invertible if and only if the rank of A equals n. And conceptually here, this kind of makes sense because basically you can take this inverse if and only if the thing doesn't lose dimension, right? We've talked about how, it doesn't make sense to take, say, vectors on a line and pull them into two-dimensional space and somehow know where they were. We don't know the information to go backwards if it's stuff like that, which would be something that's not invertible. I'm also going to note, so last time we proved that the rank of ATA is equal to the rank of A, right? And so if we can show that, assuming ATA is invertible, we get that the rank of ATA is n, then the rank of A is also n, right? So basically I'm going to work with ATA and note we've already shown that ATA is equal to the rank of that is equal to the rank of A. So it's going to let us get this, basically. Okay, let's just jump into it. So So we know, we've talked about this idea where, just formally, I kind of said it 2 seconds ago, but the idea that ATA is invertible if and only if the determinant of that matrix is not 0, right? And so we can use that, all right? So the forward direction, we're going to assume ATA is invertible and show the rank of ATA, i.e. rank of A, equals n, okay? And we are going to use proof by contradiction. So assume, don't really need capital A there, the rank of ATA is less than n, all right? So we're saying it's basically we're assuming, what if it wasn't full rank? What would happen? Then there must be at least one 0 row. So the determinant of that ATA matrix must equal 0, right? If you did a determinant in any matrix where there's 0 row, when you expand along that, you're going to kill off like all the cofactors, and the thing will be 0. And this, is a contradiction to our knowledge that determinant of ATA doesn't equal 0. Okay, so that means that we've proven the first direction, right? So for the reverse direction, pretty similar. So we're going to assume the rank of ATA, which is the rank of A, right, by our previous proof. Assume that thing is equal to n, so full rank, and show ATA is invertible. All right. And we're going to use contradiction again. So using contradiction, assume ATA is not invertible, which would imply that the determinant of that matrix is equal to 0. All right. And we know it's basically the green stuff in reverse. We know this can only happen if ATA is not full rank, which is a contradiction. Okay? And I'm not gonna, really, if I was formally proving everything up, I'd probably fill in a little bit of other stuff in there, just say like, since we've contradicted it, this means that what we assumed is wrong, and yada, yada, yada. But that's definitely the idea of this one. So, few important things here. Even though they're talking about ATA here and they're talking about A here, remember that the ranks are equal, okay? And this is a very important result that we're using like the whole time. So something's only invertible if its determinant is non-zero, right? Basically, if this equals 0, then the transformation is losing some dimension. So you're going to have like less rank, basically. Okay, so just one more. I want to prove that the rank of AB product is less than or equal to the minimum of the rank of A or comma the rank of B. So whichever one is smaller here, basically I'm saying the rank of this thing is less than or equal to that one, whichever one is smaller. All right, so to do something like this, we actually kind of need to do it in like cases. So case 1, I'm going to prove rank of AB is less than or equal to rank of A. And then the other one I'm going to prove is rank of AB less than or equal to rank of B. And so if you've proven both those, then you've proven that it's less than or equal to the minimum. All right, so to start off, I'm going to let, I'll call it B1 through like B, I don't know, P or something, denote the columns of B. Then we have A times B could equal this is like the matrix column expansion thing that we saw when we first did partitions. So AB1 and then like all the way up to whatever ABP is. Right, just do it basically, just saying all of them, right? So then each ABI is in the column space of A, yeah. And that's just because of this case right here, okay? Then we could say, so the column space of AB is contained in the column space of A, all right? And we know that, rank is just the dimension of the row or column space. So since rank is just the dimension of the column, I should probably just put this in words, is the dimension of the column or row space for a matrix, we get that the rank of AB has to be, like this is a containment symbol, so it's like the curvy one, but now this is truly like a numerical representation, right? So the rank of AB would be less than or equal to the rank of A. All right, so now case 2, all right, we're going to show that the rank of AB is less than or equal to the rank of B. All right, so to do this, we're going to take, so rank of AB, and we showed last time that the rank of a matrix is equal to the rank of its transpose. It doesn't matter which way you look at it, rows or columns are equal. The dimension of those, the row space and the column space are equal. So this would equal the rank of AB transpose, right? Which would equal the rank of B transpose A transpose, just using like transpose properties, right? Do that like socks and shoes thing. And I think I'll just kind of pause there for a second. So, maybe I shouldn't have done like all these cases because it's kind of weird because now I'm going to like reference this thing. Really, these are like separate things, and I did just show that the rank of AB is, I proved that the rank of AB is less than or equal to the rank of A. So like I do technically have that to work with here. So I'm basically going to utilize this, okay? And what this is just saying is that the rank of a product of matrices is always less than or equal to the rank of, like that first one there, right? And so I'm going to say using green, very formal proof technique, above, we let B transpose, like basically B identifies A, and A transpose B identifies B. So we get that the rank of B transpose A transpose is less than or equal to the rank of B transpose. All right. And now I'm going to kind of pop back to, so actually use this idea again, but now I'm kind of going from transpose back to here. So since rank of B transpose is equal to rank of B, we've shown that rank of, I don't know why I'm capitalizing this. Rank of, AB is less than or equal to, the less than or equal to pops up right there. Okay? Less than or equal to rank B. And basically proving both, I think I'd rather call them parts, maybe, kind of A and B. So I'm going to retroactively put a B here and an A here, proves the result. And that's it. Okay. This whole problem, you should basically just be thinking, rank is dimension of row or column space, and that's basically what we're doing. So these are just like a few kind of trickier, I would say, rank kind of proofs that I just wanted you to see.